regarding the sessions. Maz will be answering them at the end of the session, or you can just type those questions in the chat box area. So I can ask those questions Maz directly. Okay, so we shall be starting. Hello and welcome everyone to day two of our machine learning paper clubs, reading clubs. We are excited to continue our exploration of groundbreaking research and innovative ideas in the field of machine learning. And today we will delve into one of the most influential papers in recent years. Attention is all you need. The paper has revolutionized the way we approach natural language processing and the other areas of AI. We are thrilled to have an esteemed guest speaker who brings a wealth of experience and insight into our discussion. Please welcome Maaz Ali Nadeem, the co founder and the CEO of Vector, who will be sharing his perspective on this transformative work. Over to you, Maz.
Thank you, Kaina. Thank you for that amazing introduction. Assalamu alaikum, everyone. This is Maaz Ali Nadeem. I hope I'm audible to you all. Just give me a thumbs up or something. Wonderful. Um, I don't know. I'm not going to talk much about the paper because let's just say it's by far the most influential thing that there is in AI. And I'll just delve into what it is, right? Let me know when you can see it. I guess you can. Can anyone let me know if they can see it? Perhaps unmute yourself because I can't go back to my screen. Or should I? Yeah. Okay, perfect. Okay. Um, so, thank you to the TensorFlow user group Islamabad for having me again. My name is Maz, as Kainat mentioned before. And the paper we're going to study or know about today is attention is all you need. So in this particular paper, your attention is all I need for this entire session, right? um, I've co-authored a couple of NLP papers as well, and attention perhaps brings that most important factor that no other neural network can bring, right? And we're going to sort of delve into that today. Let me know if anyone knows about recurrent neural networks. Is there anyone who knows about RNNs? Because we're gonna understand why RNNs are not good. Anyone? Yeah, Pratima Singh and Shiraz, please unmute yourself one by one and let's hear you guys. You guys can unmute yourself and quickly share.
Assalamu alaikum, sir. The RNN is used for data set. We are like a stock market, and the RNN majorly used for predicting a data from previous data, like a stock market data set. Am I right or wrong?
You're partially correct. There's a bit more, explanation to it, so I'll dive into it. Pratima, please, you raise your hand as well. Pratima, can you hear me? Okay, I think she's not accessible right now. Right, so a recurrent neural network basically was, um, let's just say it was a better neural network model as compared to previous machine learning approaches to model sequential data. So sequence could be stock markets, as Shiraz rightfully pointed out, but sequence could also be words, right? And that is why recurrent neural networks were majorly used for all of these language tasks, right? However, we would start with a zero state, and then we would take a word. We would know what this previous state was, which was none in the beginning. We would take the word, we would make a prediction, and then we would use that state and a new word to make another prediction. Let's just say that this is your word in English, and you're doing like a translation task from English to French, but it's happening at different time steps, right? So it's happening word by word. So you take in a word, you give an output, you take a state, and then you take another word and you give another output, and so on and so forth until your input words are done, right? And this happens at different time steps, which means that it's sort of like a for loop that you cannot parallelize. Until this thing is done, you cannot do this, right? And then until this state is not reached, you cannot go to the next state. And this is a sequential model that is really long in its computation, right? You cannot make it parallel in any ways. And if the chain is too big, you can have a problem of vanishing or exploding gradients. Now, what does vanishing or exploding gradient means? Let me explain that to you. Ignore this diagram for now. Look at this one. Let's say that your model is pretty simple, right? This computational graph is of a very simple neural network, which could be a very small or a very simple example of an RNN. You have two inputs, right? I say that my first computation of this graph is a function f of xy is equal to x times y, right? And then it gives me an output which I call z, and I send it inside another node of computation, which is a g of z is equal to z square, right? This is my entire computation for a very simple neural network. Now, if I want to find the derivative with respect to this function all the way down to my x, which is my input value, I have a chain, right? So it's called the chain rule in calculus, where I say, hey, I want a dy with respect to df, it's a derivative of y with respect to the function f, multiplied by the derivative of function f with respect to x, so that I can get dg over dx. And I assume that this gradient is a zero point 0.5, and then this gradient is also a zero point 0.5. When I multiply them together in this chain rule, it becomes 1 by 4, which is a 0.25, right? Now, can someone answer me, if we have 50 of these nodes and all of the gradients are zero point 0.5, what would the value be? Let's say we have 50 of these nodes. This is my 50th node, and we have like 49 nodes here as well for computation. And I want to go all the way back till my input. What would the value be? Zero point 0.5 is the gradient for each of the nodes, and we have 50 nodes. Can anyone tell me the value, or can anyone tell me how we would compute that? Anyone? Okay,
बहुत
no one.
insignificant value हमारे पास आ जाएगी, like बहुत close to, very
True.
close to zero.
Yeah, and why is that? Because what? Let me just write it down over here, right? So we only had two nodes here, and I'm just assuming that the gradients for all of these nodes are 0.5, right? So it's a 0.5 square for the example that we just did, right? We're multiplying 0.5 by 0.5, but if we have 50 of these nodes, and assumingly if all of these nodes are really, you know, all of these nodes have the same gradient, which is 0.5, we would be multiplying 0.5 with itself 50 times, right? And for that to happen, I don't know if I can even compute it here, but can anyone tell me what a 0.5 raised to the power 50 would look like? 0.5 raised to the power 50. What would that look like? Solly, are you computing it? 8.88 10 power minus 16. Oh, so it's 8.88 10 raised to the power minus 16, right? And if I have 100 of these, the value would go below the level of precision, which is a 32-bit precision for most of our computers, and it would primarily just be zero, right? And if you have really long sequences, let's say you have 150 words, which is something that's very common for a paragraph. If you want to translate a 150 word paragraph into French from English, you would perhaps be looking at really, really small gradients. All of them are multiplied together and they go to zero, right? So that's called vanishing gradients. But at the same time, if you have like really big gradients, let's say my current gradient is 25 and some other gradient is like 30, and then if we keep multiplying really big gradients together, that's called the exploding gradient problem, right? And in RNN you could not really control this. Even for LSTMs we did have a memory cell, but if you are looking at an elongated example, it would lose the meaning of the words that it saw before. Here, let me show you an example. So what it does is it loses meaning in long sequences, right? So this is an input sentence which called, don't eat the delicious looking pasta because the pasta and the pizza have been in the fridge for too long, right? This perhaps means that they're rotten, or they've expired or whatever. And let's say that as our RNN proceeds, it loses the meaning or the understanding of this particular word, don't, right? and it's because it's too long and it's starting to lose its meaning. This perhaps has zeroed out or something. So what happens is that our current state knows ate the delicious looking pasta because the pasta and the pizza have been in the fridge for too long. It has forgotten don't because it has been too long and away in the sequence. And this literally means opposite, right? We want the person or the machine to not to understand that we should not eat that pasta and the pizza, right? But as the sequence has really grown, we forgot the don't, right? And we can't really make this happen. So we need to understand that this don't relates to this pizza and this pasta, right? And it relates to all of these other words. And that is why we welcome the transformer architecture, where we give an input, we have an output, and what happens in between is black box until now, but we're going to unveil that right now, right? So in the transformer, we basically have two blocks. One is the encoder block, one is the decoder block. This is what the architecture looks like. This part of the architecture is the encoder. The encoder gives some inputs to the decoder, and this entire red area is known as the decoder itself. This is where we find out the output probabilities and we start auto-regressively spitting out words and the answers in the inference, right? Um, I was about, oh yeah, one thing that we're going to also look at is there's this term, it's called NX in the paper. Can anyone tell me if they know what this NX represents? Osama, even for LSTM and GRU, really long sequences would start to lose their meaning. Although the memory cell is there, but the memory cell would also start to die out when the sequences are really long. It's better than RNN, but it's again not good as a transformer. Furkan is absolutely correct. NX represents six encoders over each other. You're right. So in the actual architecture, however, the architecture here seen is pretty simple. This encoder functionality is to be replicated six times, and this decoder functionality would also be replicated six times in the actual transformer, and this is just a hyperparameter, right? You could change it to 2, you could change it to 20. The authors just found n to be 6 as the most optimal performance, right? And that is why they chose n to be 6. Right. So before we go ahead, I just want you to ensure that you know matrix multiplication. Let's say if you have a matrix of 6 by 512, which in our case or in our example would be, um, we would be taking six input words and we would be generating 512 embedding values for each of the words, right? And if you multiply it by its transpose, which is going to be a 512 by 6, what should be the output matrix? It should be a 6 by 6. I'm sure you all know matrix multiplication because it's one of the most fundamental concepts to know neural networks. 6 by 6. Wonderful, Furkan. That's exactly right. Right, so your input matrix would have two dimensions. The sequence basically means the number of words, which in our example that we're going to take would be 6. And the dimension of the model, the dimension model means how many letters or values are we using to represent one word. And in our case it's going to be 512, right? So a vector of 512 embeddings would be representing one word, right? And let me explain to you what input embeddings look like in the encoder architecture. So you have this sentence, it's called your cat is a lovely cat. This word, which is now considered to be a token, I am simplifying the tokenization aspect. um, we have a corresponding input ID in the vocabulary, right? So we know all of the words in the English dictionary, and in our dictionary these are the positions of those words in a linear dictionary, let's say, right? And we're learning how to embed them into 512 vectors, right? So they're embedded in terms of meaning, and I'll give you a little more simplistic example in the next slide. So what we do is we convert these words into 512 embeddings, right? A vector of 512 values. And what you're going to see is that the same word, which is cat here and here, will have the same embedding, right? So right now what we're getting from the input embedding part is we're understanding the meaning of the word at the individual level, right? And you can see here, and this Oh, I have a very terrible typo over here. I'm sorry about that. Right. Can anyone answer me in this particular embedding space? Where would you put the word apple? Would it be in A? Would it be in C? Or would it be in B? Or perhaps D? Can anyone answer me this question? C. That's a fair answer. Anyone else? Can you tell me if I was to place the word apple in this embedding space, where would I put it? C. Yeah. Why? Because we see that in an embedding space, all of the things that relate together are placed very close to each other, right? So anything that relates to sports would go here. Anything that relates to fruits would be closer here, right? Anything that relates to transport would be in this embedding space, and anything that goes to like housing or buildings would be in this space, right? So in terms of Apple, this is where we would place it because we know the meaning of it right now, right? But let me present a few more questions to you a bit later. Now, one thing is the understanding of the meaning that we find through the embeddings, right? The input embeddings. Now, there's one more thing which is called the positional encoding. Positional encoding adds the understanding of where your particular word is in the sentence. Your cat is a lovely cat. The placement of this, the position of the word matters equally along with the meaning, right? If cat was to be placed in the first position and yours would to be placed in the second position, it would slightly have a different meaning in terms of a sentence structure, right? So what we do is we calculate some positional embeddings, we add them to our actual word embeddings, and now we have an encoder input, right? So now we know two things. What does the word mean at the individual level, and where is it relatively placed in the sentence? And how do we calculate position embeddings? This is the function. So for simplicity, I've broken the sentence down to only three words. Your cat is, right? So your is the zeroth position of the sentence. So what we do is for all of the even numbers, which is 0, 2, 4, for all of the even positions, we use this function as given in the paper, right? The only two things that we send is the position of your word, which in this case is 0, and the current position in the vector, right, which is also 0 for the first one. So it is pe 0 comma 0, and we use this formula to find the positional encoding value for this particular cell. And then we go down and we go all the way down till 512th place in the vector. And then we have the second one, which is cat. And here you see that the positional embedding is going to be 1 comma 0. Why? Because cat is the second letter of the sentence. And then we're going to find embeddings for all of the vector spaces in particular, right? And this is for the odd numbers. 1, 3, perhaps the last one, right? So odd and even, this is how we divide it. And there's one thing, we only need to compute these positional encodings once because we can reuse them. So let's say there's another sentence that says I love you. These positional encodings would remain the same because positionally I is at the same place where your was and love is at the same place where cat was, right? So you won't need to compute them again and again. And that's that. um, and now comes the actual part, which is the single head self attention. Look at the function over here, and we're going to visually look at it right now. So, in order to compute attention, you have three matrices Q, K, and V. Q, K, and V are just the same matrices as the input sentence, which would be of the sequence length 6 by 512. We saw this example here before, right here. So we have six words, those six words, and each word has 512 vector embedding, right? And that is pretty much it, right? What we do is we replicate Q, K, and V with the same values. And now what we do is I'm going to first explain to you self-attention and then we're going to look at multi-head attention, right? So according to this formula, what we're doing is we're multiplying the we're multiplying q by k transpose, right? So q is 6 by 512. K transpose is going to be 512 by 6, right? So query key and value. Do we have a question? In the cos and sine function, what does the denote? Oh, okay, let me. Oh, it's the D model. D model was 512, which is the dimension of how many vector embeddings we have, the dimension of the vector embeddings. Samila, do you have a question? Okay, I think we'll proceed with that. So what happens is that we multiply q by kt. Now these are the same values, and we, in order to normalize it, we divide it with. Yes, Samila, do you have a question? Hello. Why we use other functions like tan and other? We're not using tan or the other function here. We're using sine and cos because like we see in our visual senses, we like sequence to be like 1 2 3 4 5 6 7 8, right? But in the geometric terms, sine and cosine have better, they have a better geometric representation that the computers can see in terms of how the numbers are placed. And that is why the authors also primarily discuss q and t in our case. Okay, so now what we do is we take an under root of the dk is basically uh, the the value of, um, it's the value of how many vectors we have, sorry, how many elements we have in the vector, which is again 512, and we take a softmax of it. So the softmax, basically what it does it is that it gives you all of these row sums to be 1, and you can sort of use it in a probabilistic manner to feed it into the neural network. Okay, so what we have here right now is sort of a relatability matrix between the words your cat is a lovely cat, word by word relatability, right? um, and after we have this, which is this part.
अच्छा
Samuela, can you please mute your. Guys, does anyone have admin access? Okay, I think we should be able to proceed now. Can you guys hear me again? Just please confirm so we can proceed. Okay, wonderful. Right. Given this attention formula, we've done half of it right now. So we have a 6 by 6, and then we multiply it with V, which was again the same input matrix, just given a different name. And when we multiply the 6 by 6 matrix with the V matrix, which is 6 by 512, we get an attention matrix, right? And this is a single head self attention. What happens here is each row in this matrix not only now captures the meaning we found out by the input embeddings, which was only at that particular word level, we also do not only know the position of the sentence, which we found out by the positional embeddings, but we also now know how each word is interacting with the other word, right? And I'll explain to you why multi-head is important after this. So right now, just assume that we know how each word relates to all of the other words in one way or the other in the context, right? And now look at this formula really closely of multi-head attention. So this was what we did for attention. For the attention function, we take in three matrices, which is called a Q, a K, and a V, and we apply a softmax to the multiplication of Q times V over a normalization under root dk, and then we multiply that with V. In multi-head, we take the same inputs, which is called Q, K, and V, and the function is to concatenate different heads together and multiply them with some weight matrix, right? Now, what is going inside this head? It's this attention function, but we do not use these q, k, and v values raw because they are basically just the input values. We need to attach some association of weights to it, right? And the only reason why we need to attach that, then we would be able to update our learning like in any neural network, because that's how we update the weights in a neural network and adapt the architecture to be in a manner that is able to fit the data, right? So now our attention would not just be q, k, and v. There would be some multiplicative forms with a matrix of a weight, right? So what happens now in multi-head attention is you have the same input, right, that we had before, this exact input, this one, right, which is 6 words and 512 vector embeddings for each word. That's it, right? This is your input. What you do is divide it into you don't divide it, you basically copy it into three different names. One is called query, one is called key, and one is called value. And what then happens is you multiply each of these matrices with some weight matrices that are initially randomly initialized, right? And we use basically back propagation to be able to find the best values for W and W here, right? For to find the best weights that should be multiplied with the input, right? And so we multiply them together. Q times WQ, K times WK, V times WV, right? What then happens is we find some new Q, K, and V values. And these are now multiplied with like randomly initialized weights, right? Just like a neural network, because this is how we do it in a simple feed forward neural network as well. We have the input, we multiply them with random weights, and then we're able to sort of keep updating the weights together, right? Now, the main part, which is that you have this Q. Previously, what you saw was that we were multiplying the Q with the K, right? And then we were basically following the attention formula altogether. Now we're going to divide it. So in the context of the paper, the D model, which was basically 512 features, what we're now doing is we're dividing them by a value h. The value h in the paper is 4, right? So we have 4 divisions of the 512 embeddings. So what happens now is we send it to different heads. So we have 8 heads in the actual paper. What happens here is every head gets to see every word, but not the entire embedding, but rather a part of the embedding only, right? And they get to see all of these, the K, the V, and all of these parts at different, only that part of embedding. Like the first 128 values of the embedding, the second 128 is seen by a different head, the third 128 is seen by a different head, and the fourth 128 is seen by a different head altogether, right? Um, so what then happens is then I will show that to you right now. So what you now do is you multiply the q with the k, you apply a softmax to it as we applied here, and we now multiply it with v, and we find the head, right? So now we have head 1, head 2, head 3, and head 4. Previously, with this function that we did, we only had one head in the previous example that I showed you. Now we have 4 heads. What happens to all of those 4 heads is you concatenate them together. This is the concat function. We concatenate them all together. We multiply them by a weight O, which is again a matrix that would be applied as a weight matrix to the head, and this gives you your multi-head attention matrix, right? And let's see why that's important. Can you look at this particular figure and understand the problem? Because we have an embedding space that represents fruits well, and then we have an embedding space that represents these technology companies really well. And now we need to place Apple, right? And in terms of just the word embeddings, we would not be able to understand if the apple in the sentence, because it's an individual meaning understanding, right? I want to understand the meaning of apple. I do not know if you're talking about the brand Apple, the iPhone brand, or are we talking about the actual fruit apple, right? And this is why embeddings are not enough. This is why we need attention. Why? Because look at these two examples. Please buy an apple and some oranges from the store. Sorry, again, another typo. I really apologize for that. um, and we have another sentence which says Apple unveiled their new iPhone. Now, based on just the context of how Apple is related to all of these other words, we are able to pull the embedding towards a particular space, right? In this case, we say that this apple means a fruit because it's related to this word orange, and we're supposed to buy both of these things, right? So we can sort of pull that embedding towards orange, right? And then in this example, apple is connected, or is related to phone, and we can sort of pull that embedding towards the phone, right? And this is why you need attention to give meaning of this word on the basis of all of the other words. Now, why did we do multi-head? Look at this example, which is the animal did not cross the road because it was too tired, right? The animal did not cross the road because it was too tired, right? Firstly, in this case, the it needs to refer to the animal, not the street, right? What would have happened if it was the animal did not cross the road because it was too slippery? The same it would be relating to the street now and not to the animal, right? But in our case, let's see why we need a multi-head attention. So this is a single head attention, where if we look at it, it's sort of only relating to the animal, right? And it's not relating to the tired word, although this it refers to the animal, and this tired also refers to the animal as well. So a single head attention is not able to understand all of these different relations like adjectives, nouns, and verbs, and how they're related in the sentence, right? So let's say if we had two heads, it would look something like this, right? One head would be more focused towards the noun pairs, the other head would be more focused towards the and this is all random, right? Um, so if you look at the first head, it relates the it word to animal, and if we look at the second head, it is relating the it word to tired more, right? So it's understanding different parts of the sentence and how they contextually and grammatically relate together, right? And according to the paper, we have eight heads. So if we had eight heads, look at what would happen. In the first head, the it would be related with the animal. In the second head, the it would be related to tired. In the third head, or sorry, in the last head, it would be relating to the cross. The animal did not cross, so the cross word is also related to the animal because the animal did not cross the street, right? So we need to relate every word with every other word, and that is why a multi-head attention is able to understand a lot of very different relationships with each word to the other, right? Why do we have this key pair and this key value query pair? um, if anyone has run databases, you would know that in a database we store the words and or the data as key and values. For simplicity, we only have one value per key. But let's just say that I was to perhaps write a query like, hey, I want a movie about love. What would that do? It would first look at the embedding space and it would say that, hey, love is the closest word to romantic, and it would perhaps also be a little close to comedy, but it would not be close to horror or sci-fi or action at all, right? and then on the basis of what we have in the romantic, we would be extracting that value, right? And this is the concept within transformers as well that is being used to give the attention scores and everything, right? So now we look at the decoder part. So decoder is taking in input as of keys and values from the encoder, and it is giving the query value from the masked multi-head attention. And I'll explain that to you why. So when we want to predict the next word in a sequence, right? Like your cat, what should the next word be? It should be is. In order to learn that pattern effectively, the model needs to be causal, right? It needs to be able to explain why the next word was is, right? And in order to do that, it should not be able to look at the next word, right? It should not be able to know that, hey, this is the correct next word. It should only be able to know, hey, your only two words that you have right now is your cat, make a prediction. When it makes a prediction, only then you give it a feedback if it was right or not, right? And the model should not be able to see future words. So in a masked multi-head attention, what we do is, in the same sort of attention block, we make all of these zero, right? So you cannot look ahead in the attention space. You are only needed to attend to the back when you're decoding in the transformer and giving an output, so that your entire understanding is on the basis of what you saw before and not what you're going to see ahead, because what you're going to see ahead is based on what you predict ahead, right? And this masked multi-attention output is given as a query. Now, let's take an example of how we train the transformer. So, what happens here is we have an English sentence called I love you very much. And I don't know if this should be Italian. It's ti amo molto. Okay. So, firstly, what we do is we prepend and append two more tokens into it. One is the start. So, this is called start of sentence. I'm sorry. Yeah, this is called SOS, start of sentence. This is called end of sentence, EOS, right? So now we have two more tokens that tells us, hey, this is where this sentence starts and this is where it ends. So what happens is this particular sentence is parsed through the encoder input. It then goes through the entire encoder block and it gives you an encoder output, right? This entire thing runs through here. It gets the positional encoding, it gets the input embeddings, it then goes through the attention blocks, and then it gives you an encoder output, right? What then happens is we also start to send T molto, which is because right now we're training it and we know what the translation is. We send it through the decoder block with one output shifted to the right because we have prepended start of the sequence. We need to now predict the end of the sequence, right? Sort of we need to understand how to predict the end of the sequence along with all of these words. So what happens now is this entire Tiamo Molto goes through the decoder block all the way to softmax, and then softmax is able to understand how to predict T and then amo and then molto and then end of sentence. Once we get the end of sentence, the transformer learns that it does not need to generate any other word, right? And this entire training process was done in one time step. It was not a for loop. It was all done in parallel. The encoder input of the actual English word and the decoder input of the actual English word, they were given simultaneously. The attentions were calculated, and then encoder was done with its part, and it gave all of the inputs to decoder. That in the same time step learned how to model the input with the output. Right? It was not a step by step one word after the other for loop process. It was a parallel process. Right? And this was how we trained the transformer. Now, if you look at the inference, we need to infer this now. I love you very much, and we need to infer it into ti amo molto, right? Now, inference is not parallel. Inference is autoregressive, which means it is one word at a time, and then the word goes on the input, and then the next word is predicted, and both of them go as the input, and the next is predicted. So let's see how that is happening. So we have time step one where we give the input, we find the encoder inputs, we do the encoder calculations, and we give the encoder output. And in terms of inference, we only start with one token, which is the start of sequence token, right? And what we do is we pass it through the decoder input, we pass it through the decoder block, we pass it through all of these other calculations, and we select a token from the vocabulary that corresponds to the position of the token with maximum value. What does this mean? So your linear, the feed forward neural network is basically there to predict a probability score for all of the words in the dictionary that you know, right? And it says that, hey, this particular word on some XYZ index has the most probability of being the right word. So we just take that right word, which in our case here is going to be T, and we give that as the first output, right? That this is the first word of the sentence. Then we go to timestamp 2, right? And here we do not need to calculate the encoder again. Why? Because we've done it already and the input is the same. So the entire encoder output is also going to be the same. So from now onwards, we're going to skip the entire encoder calculation part from time step 2. So what we do now is we take the start of sequence and we append the previously generated word to it, and we pass it through the same process. Now, based on this input, it gives you another word as the output, right? Ammo, right? And now what you do is you go to time step 3. You don't again need to calculate anything in the encoder input, but what happens here is now you have sentence start of sentence, the ammo, right? And it goes all the way up. It starts to predict molto, and you go to time step 4. Now you have the sentence, start of sentence, Tiamo molto, and it goes through the entire process again, and now it predicts end of sentence. This is where the transformer knows that it does not need to generate anything else anymore. And there are two strategies for inference as well. The first strategy is called the greedy strategy, which is that we only select the best word that would in so the example that I gave you, this was the best word, right? So end of sentence was the best word, uh molto was the best word, ammo was the best word, t was the best word, which means that this strategy is called greedy, and you only get one output, one possible output. But there's a better strategy. It's called the beam search. What we do in this strategy is we select at each step the top B words. Like, we don't just select the best word, we select, let's say, the top 5 best words, and we, given those 5 words, we evaluate how the sentences would be made differently for given each of the word, right? And we get a lot of we get a lot of possible sentences then, and then we choose which of those is the best, right? This is again how the transformer infers. It's a different strategy. It's also commonly used along with greedy, but both of them have their own sort of pros and cons. Because in a beam search, you would have so many sentences in the end that it would be hard to rank the best one, right? Again, that depends on how you, or how the code that you write does that, right? And this is primarily it from me. If you have any questions, and if I do not know the answers to them, we will ask a transformer model together. So we have about 5 minutes for the call, and I think that's enough for the questions as well. Peter Basalisha has asked, in what scenarios might single head attention be preferred over multi head attention? Um, Honestly, if you just need to, well, multi head is obviously the best, but single head again only does one part of the job, right? I would not prefer it over multi head, unless you want to save a lot of compute time, I guess. But again, compute isn't a very big problem as well. Yes, anyone is YM2A. What's your question?
Assalamualaikum Maaz bhai, wonderful session. First of all, it was all very clearly explained. My
Thank you so
question
much.
was, I am very new to reading research papers. So, for example, अगर एक paper में कोई 20 references है ना, to understand one paper, I have to go through entire 20 papers, जो reference papers होते हैं, because मुझे ना वो concept नहीं समझ आ रहा था बिल्कुल भी. So, is there a more efficient way to go about this?
Can you sort of reiterate, क्योंकि आपकी आवाज बीच में कट गई थी.
Yeah, I was saying कि अगर मैं एक paper पढ़ूँगा ना, and it has references, right? और अगर एक paper में कोई 20 references हैं, So I'll have to go through 20 papers just to understand a single paper. So that takes a lot of time. Is there a more efficient way to go about this?
Honestly, no. Reading is like the best way out. But what you can do is there are a lot of AI tools out there right now that I was actually searching for one of them. I don't remember its name anymore, but it's a really nice tool. What it does is it it you give it the name of the paper and it only brings out all of those really important points that you want from the paper. But at the very end, it also links you up to all of these other tools that or a lot of these other really relevant things that you need to read, and they're also all summarized. um,
Right.
Honestly, the best way would be to go about finding an AI tool that is able to summarize the papers for you, because reading all of the 20 papers from a reference list would also not be the right approach, because um, a lot of those reference papers do not add a lot of value, right?
True.
Only some of them do, right? So you need to really see which ones. Like in the case of attention is all you need, they have a lot of reference papers attached to it too, but I think this is the best paper that you can look into. Also, a better approach I like to do is I like to learn about the papers from YouTube more, because it's a lot more visualized, better communicated, and someone compresses and summarizes everything for you. So this is how I prepared for this session, and this is how I've actually learned Transformers as well. Read the entire um, I've never read the entire Attention Is All You Need paper.
Right. Makes sense. Thank you so much.
You're welcome. What you can do is read the papers on archive at MS Edge, and while you read, MS Copilot helps you answer this question. That's amazing, Solid. It's an amazing add-on. My question is that I want to enhance my knowledge in the field of MLD and Gen AI and need to be updated on recent work being doing. I feel I should read research papers on this article, but no proper sources. Honestly, Zohaib, there's internet is honestly all you need, and in that case, YouTube is all you need. Um, I would just recommend go through YouTube. If you want to learn how to code for machine learning and deep learning, Free Code Camp has a lot of really good stuff. But Google's resources on TensorFlow are also amazing. I think Ali is in the call, would also be able to add on to that. But oh, guys, I'm so sorry. The call is about to end. I hope you all enjoyed. Please connect with me real quick, wherever Instagram or LinkedIn. I would love to answer your questions. Thank you so much. Allah Hafiz.